Let's take a look at the linked blocking queue in Java. Imagine a queue, a line of people waiting for their turn. In Java, the linked blocking queue is like such a line. But instead of people, it holds data elements. It's a special kind of queue that's designed to be safe for multiple threads to use at the same time. The queue is made up of links, like a chain, where each link holds the data of one data element. It can grow as big as needed, so there's no limit of how much data it can store. When you want to add something to the queue, it's like getting in line at the end. When you want to take something out, it's like taking out the first person in line. We also just described the FIFO principle. FIFO stands for first in, first out. It's a principle or method where the first items to be added to the system or group are the first ones to be removed. One of the great things about the linked blocking queue is that it's designed to handle situations where threads might be waiting for data. If a thread tries to take something out of an empty queue, it will wait until there's something available. Similarly, if a thread tries to add something to a full queue, it will wait until there's space. This helps to prevent errors and ensures that data flows smoothly between threads. Unlike some other blocking queue implementations, the linked blocking queue does not have a fixed capacity. This means that it can grow dynamically to accommodate any number of elements, making it suitable for scenarios where the queue size is unpredictable. While it's primarily unbounded, you can optionally set a maximum capacity for the queue, providing flexibility for scenarios where you need to control its size. The linked blocking queue uses a linked list to store its elements, which can be more efficient for certain operations, especially insertions and removals. In short, the linked blocking queue is a versatile and reliable tool for managing data in concurrent programming. It's perfect for situations where you need a thread-safe, unbounded queue that can handle a large volume of data. So how does the linked blocking queue compete against the array blocking queue? Well, the linked blocking queue can dynamically adjust its capacity as needed. This eliminates the need to predetermine a fixed capacity, which can be challenging in scenarios where the load is unpredictable. Growing or shrinking to accommodate a workload like this is not possible with the array blocking queue due to its fixed capacity set. Also, the linked blocking queue can potentially reduce contention among threads, as the in-queue and dequeue operations are more localized. To sum up the comparison, the linked blocking queue can outperform the array blocking queue in scenarios with high concurrency, unpredictable workloads, or when the queue size frequently fluctuates. The array blocking queue, though, may be more efficient in scenarios with a predictable workload and a fixed queue size. Alright, that should be enough theory. And don't worry, all the code in this video is uploaded to GitHub so that you can try it out, understand every detail, and use it in your future projects. You can find the links to the GitHub repository in the video description below. Okay, so here we have a Maven project, and we also have 2 build scripts and 2 run scripts. Now it depends on your operating system. If you work on Windows, you're going to make use of the CMD scripts for build and run. And if you work on Mac or Linux, you're going to use the shell scripts for build and run. Alright, let's start by creating a new class, example1, which implements the runnable interface. And right away, let's implement the run method and announce what we are doing, running example1. Now let's create a new variable, queue, of type LinkedBlockingQueue, which handles strings, and insert a new instance of LinkedBlockingQueue. Okay, let's start with the producer. Let's create a new variable, producer, of type thread, in which we put a new instance of thread. And as a parameter, we pass an anonymous method, in which we start by making use of the put method to add a new text, task A, to the queue. Let's make use of the put method again, and add a task B, and again to add a task C. Now you might have noticed the red underline under all these put methods. This is because we did not yet catch an error that might occur. And this is the interrupted exception that can be thrown. So let's put these 3 lines into a try-catch context. And in the case that the error happens, let's print the message producer interrupted. Alright, now let's create a consumer. Let's create a new consumer variable of type thread, in which we put a new instance of thread. Again, the thread gets a parameter, having an anonymous method, in which we start by creating a while loop, which runs as long as the queue is not empty. And here we make use of the take method to get the top element and put it into a string variable that we name element. Now let's output the element. System out print line consuming element. The tape method also might throw an error, which we can catch by creating a try-catch context for the interrupted exception. And in case that happens, let's print a text consumer interrupted. Alright, now let's consider ourselves with starting the threads. Let's first start a producer and then the consumer. Alright, let's put it together in the main method. Let's create a new variable example1 of type example1, in which we put a new instance of example1. And the only thing that we need to do now is trigger the run method. Alright, now let's take a look at what this looks in action. Let's build and run the application. And here we can see our example, showing the consumer side, which consumed task A, B, and C. Alright, let's build another class example2, which implements the runnable interface. Let's first start by creating a couple of int variables. Num elements, which we set at 1000, num producers, which we set at 4000, and num consumers, which we set at 4000. What we will do with them will become clear in just an instant. Let's first implement the run method and announce what we're doing, running example2. Now let's create a new private method, which takes blockingQueue, handling integer as a parameter. This means that this method takes as a parameter any class that implements the blockingQueue, which is the LinkedBlockingQueue, the ArrayBlockingQueue, and the PriorityBlockingQueue. Alright, but let's first remember the time that we have at this moment. For that, let's create a new variable, startTime, of type long, in which we save the current time in nanoseconds. Now let's put our attention to the producers. Let's build a new thread array that we call producers, in which we put a new instance of thread, and the number of elements that this array can take corresponds to the number of producers that we defined, which would be 4000 in our case. Now let's create a new for loop, which runs from 0 until to the number of producers, so that we traverse all the indexes in this array. And what do we want to do in these indexes? Well, in every index we want to create a new instance of thread. And as a parameter for thread, we pass on an anonymous method. And in this method, we have another for loop, which runs from 0 until to the number of elements that we defined, which is 1000 in our case. And in every possible place in the queue, we put an integer, which is in this case just the current index. The put method of the queue can return an error when it is interrupted. To catch that, we put it into a try-catch context, so that we can catch the interrupted exception. And in the case that this happens, we output a text, producer interrupted, message, and then the message of the interrupted exception. Alright, now let's put our attention to the consumers. Let's start by creating a new thread array, which we name consumers. The amount of elements in this array corresponds to the num consumers variable that we defined, which we set to 4000. Now let's create a new for loop, which runs through all the consumers, so that we can define a new thread instance for every possible consumer entry in the array. The thread gets an anonymous method, in which we have a for loop which starts at 0 and runs until to the num elements that we defined at 1000. And in every iteration, we try to take the next element. If interrupted, the take method can result in having an interrupted exception, which we can catch in a try-catch context. In the case that this happens, we print the line, consumer interrupted, message, and then the message of the interrupted exception. Alright, now we need to start all the threads. So for that, let's create another for loop, which runs through every producer that we have, and in every iteration, we start the thread that we get. Let's also do the exact same thing for the consumers by starting them all. Now they may run a while, and for the time waiting, we're gonna make use of the thread join method, running through every thread that we have and waiting for that thread to terminate. Let's do the exact same thing for the consumers as well, by joining them all. And because again, this can result in an exception, let's put it all into a try-catch context, and in the case that this happens, we print an error, join interrupted, message, and then the message of the interrupted exception. Alright, let's print some statistics. Let's first remember the new time that we have now, after having waited for all the threads to complete. For this, we're going to create a new variable int time of type long, in which we put the current system time in nanoseconds. Now let's calculate the duration, which is essentially the difference between the end time and the start time. And now we are ready to print our result. Let's first start by getting the class name, because we will test different types of blocking queues, and then took, and then the duration converted from nanoseconds to milliseconds. Alright, now let's go up to the run method and make the actual call to the test queue method, providing the LinkedBlockingQueue, the ArrayBlockingQueue, which we have to limit to the num elements, and the PriorityBlockingQueue. Alright, now let's go to the main method and put it all together. Let's create a new variable example2 of type example2, in which we put a new instance of example2. Having done so, we run it. Alright, let's build and run the application. And here we can see the result. With our setting of the num elements of 1000, the producers of 4000, and the consumers to 4000, on my system the LinkedBlockingQueue took 556 milliseconds. The ArrayBlockingQueue took 909 milliseconds. and the priority blocking queue took 3 seconds and 431 milliseconds. So the difference, in other words, is quite big. Now it would be very interesting if you could do the same tests on your system and also play around a bit with the numbers that we set. In my opinion, these numbers are quite realistic, but maybe in your case it's very different. It would be nice to know, so comment below as well. To sum up, we first checked the basics of the linked blocking queue. We also compared the linked blocking queue to the array blocking queue to see which one is best for which situation. We then created a simple code example to see its basic usage, followed by another, more extensive code example, comparing the linked blocking queue, the array blocking queue, and the priority blocking queue. Alright, that's it for the linked blocking queue. What did you think about this short introduction video? You can hit the like button if you found some value in this video. It massively helps this channel grow on YouTube. Also, you can subscribe to this channel, as it is the best way to get notified about future videos with content just like this one. Thank you very much for watching. My name is Gene. See you in the next video.